To begin, we'd like to thank the judges for taking the time to review our presentation and project, addressing the use of computational fluid dynamics to assess the efficacy of tsunami mitigations. Tsunamis are exceptionally large ocean waves that are destructive to property and deadly to people. Mitigation methods are employed as tsunami protection, but computer simulations and/or scale model laboratory experiments are necessary to ensure their effectiveness. Scale model laboratory experiments are costly, and data regarding wave behavior may be incomplete. Simulations offer a cost-effective alternative to study tsunami impact at scale. Assessment of tsunami and mitigations have previously been done. A group of researchers ran laboratory experiments of tsunami runoff on a circular island. In this study, the incoming tsunami was modeled as a solitary wave. Another group of researchers ran computer simulations of tsunami attacks on a rubble mound breakwater of Haydar Pasa Port, but direct comparison of mitigation techniques on the same geometries have not yet been studied. In order to ensure the efficacy of tsunami mitigation methods, they must be tested in a cost-effective and functional way. The goal of our project was to demonstrate the capability of computer models as a cost-effective means of assessing tsunami mitigation measures. To achieve the project goals, computational fluid dynamics was used to predict the motion of the waves through water and over land. The first step in this method is to create a computer model of the land and the surrounding water. This model is subsequently divided into cubic volumes, called cells, over which the laws of conservation of mass and momentum are enforced. The base island geometry was conical, with base and top diameters of 7.2 and 2.2 meters respectively. The vertical height was 0.625 meters. This was the island geometry studied at the U.S. Army Corps of Engineers and serves as the unmitigated case here. Seawalls are a common mitigation method for spurious ocean waves, including tsunamis. The seawall height for this study was 0.05 meters above the still water height. This height was based on the average ratio of seawall heights to tsunami heights in the Tohoku region of Japan. The length of the seawall, 60% of the island circumference, corresponds to seawall coverage for small islands. The detached rubble mound breakwater mitigates the tsunami by reflecting a portion of the wave and transmitting the remaining portion at a lower intensity. Our breakwater had a porosity of 39%, and each pebble had a 3.1 centimeter diameter. The breakwater geometry was built to have the same height as the seawall, cover 60% of the island coastline, and have a slope of 1 to 1.5. Avoiding aesthetic issues associated with the seawall and mechanical issues associated with the breakwater, the cylinder wall seeks to capture features of these mitigation methods. This mitigation method of our own design was constructed by making 24 columns, 0.5 meters in diameter, with gaps in between to transmit waves. As with the seawall and breakwater, the cylinder wall height was 0.05 meters above the still water height and covered 60% of the island coastline. The procedure we followed in our simulation study is shown in the flowchart. First, the island model and mitigation structures were constructed and the computational mesh was generated. Next, initial and boundary conditions were specified. Notably, in the scale model, the incoming wave height was set to 6.4 centimeters. Also, probe locations were defined where water surface height and total pressures were set to be recorded at tenth of a second intervals. The entire water surface shape was recorded at tenth of a second intervals as well. The model was run using OpenFOAM's interfoam solver. Each simulation advanced in time using an automatic time-stepping procedure, and simulations were stopped after 15 seconds of simulated time. This corresponds to the time required for the wave to reach the opposite end of the wave tank. Finally, results from the simulation were analyzed by creating surface motion animations and plots of water surface elevation and total pressure. From the surface motion animations, unexpected leeward side runoff was observed, as shown in the images. Progressing from left to right, runoff was first observed on the seaward side of the island, as expected. Following the initial contact with the seaward side, the wave divides and runs along the island circumference, recombining on the leeward side, resulting in leeward side runoff. Comparative plots displaying water surface elevation just above the still water surface on the seaward and leeward sides of the island are shown. The plot on the left shows that the cylinder wall offers little mitigation. Additionally, it's ineffective at slowing the arriving wave. The seawall mitigation is not appreciable, but wave arrival is delayed. Finally, the breakwater mitigates the wave substantially, reducing the water surface above the island and provides a slight arrival delay. Turning to the leeward side of the island, the plot on the right shows that no mitigation strategy is effective against leeward side runup. Since pressure is force per unit area, force and pressure are proportional. Plots here show the total pressure at ground level on the seaward and leeward sides of the island just above the still water surface. The plot on the left shows that the seawall provides no force reduction, the cylinder wall slightly reduces force, and breakwater reduces force substantially. Looking at the plot on the right, the breakwater is the only mitigation method that reduces lee side wave forces. As expected, the unmitigated case exhibits seaward side runup, and it's concluded that the seaward side can be partially protected using breakwaters. The unmitigated case also exhibits unexpected leeward side runup, and none of the mitigation methods could suppress the leeward side runup since none suppress wave contact and wraparound. All of the mitigation methods studied were designed to address head-on waves. However, for this island geometry, redirection of the wave is necessary to suppress leeward runup. In conclusion, breakwaters were the most effective mitigation method tested. However, small circular islands pose a unique mitigation challenge, the leeward side runup. Addressing this challenge requires novel mitigation strategies. As we continue our work, we plan to compare unmitigated results to published data, as well as simulate actual island geometries with small circular shapes, such as the Bobby, Okshiri, or Hawaiian Islands, to design and test a mitigation strategy to reduce lee side runup in these island shapes.